Alright, welcome back, Digital Electronics. Hey, we just got done talking about asynchronous counters and modulus counters and things like this. I wanted to roll through some examples for you to kind of understand what's going on here in Multisim. So I got 3 different examples that I want to go through with you, understanding how to do a count circuit and things like that. Okay, one thing I've added on here that I'm going to talk to you about in the next lecture is the 74LS47N. Alright, so that's going to take our binary code and send it to the 7-segment display, and it's going to decode all the digits for us. Alright, I'm going to talk about that in the next lecture, so don't worry about comprehending the 74LS47N right now. We're going to cover that soon, but just know that it takes our binary signals and it sends it all, decodes it to the 7-segment display for us. Alright, so notice that we're sending in a signal A, B, and C on each one of those. So that's the important part there. If you can see that A, B, and C, that comes from the Q output of the D flip-flop that you see. Alright, so that's going to toggle through, and that's going to go through our 0, 0, 0 all the way up to 1, 1, 1. Okay, so it's going to toggle through our count, so we can go from 0 to 7, right? So this is going to count through 8 bits for us when we do this. Okay, so what's important to understand here is notice that I'm going to control the count. How do you know I'm controlling the count? Because I have the NAND gate down here, right? I have the 74LS10 that's sitting down there. And remember, we have to do the count that we want to stop at plus 1 for it to cycle through. Alright, and we pull those different values that go into the count here. Alright, I'm going to run this in a second. Notice I'm tied to the clock down here. So I got a rising edge clock, and I've lowered it to 50 Hertz so that we can actually watch it cycle through. I'm connected to a common anode here, 7-segment display. I'm going to cycle this through all the D flip-flops. So notice this is asynchronous, right? Because we have one clock signal that goes into the first flip-flop, and the other clock signals are being carried from the preceding flip-flop. What I also want you to notice here, though, is that our most significant bit, very, very important. So the most significant bit here is coming out of the third flip-flop on the right. So that's my X4. When you see that probe highlight, all right, that's my most significant bit, right? It's the one that changes the least. X2 is my least significant bit. It's the one that's going to change the most. It's coming out of the first flip-flop. So you got to remember, even though these flip-flops were going left to right as we're cascading, the MSB to LSB is right to left. So you got to think about that, that backwards a little bit, because we're going to be able to control the count up and we're going to be able to control the count down, but we have to understand where our MSB and our LSB is when we do this. So very, very important when we do this. Okay, so you can see that I'm controlling the count here. So if I look at this NAND down here, I have a red that's going into X4 that's pulling out the Q. Okay, so that tells me I'm looking for a 1 right there. And then I have a red that, if I trace this back, it's going out to the X3, it's going to the Q as well, so that's a 1. Okay, and then I have this blue line, if I trace it back, it's going to Q0 out of the first flip-flop. To me, that's a 0. So I'm looking at 1, 1, 0. Okay, so that's what my control is here. 1, 1, 0 is 6. So this, should reset when we get to 6. So I'm going to go ahead and hit play here, and we can watch it as it counts through. Alright, so we had the ripple effect as well. So we're going to go 0 as it's clocking through, and you can watch up here on the probes that are going to tell you, right? And remember, MSB is different. We can see the delay in propagation, okay, because it's asynchronous and separate clocks. Okay, so we're going to go 0, 3. So notice if you're looking at MSB, so this is MSB 100, which is equal to 4. Okay, this is MSB 101, which is equal to 5. All right, and then look, it's not going to reach 6. You saw a small ripple effect at 6, but 6 is our count plus 1. So remember, I want this to count from 0 to 5, so I have to tell it to reset at 6. So that's why the reset at 6 is going in as 1, 1, okay, 0, because that's 6 in binary. That's what's going into this NAND. And notice the NAND is going into all the clears on the flip-flop. So that's my reset count. Okay, so that's taking a look. We're able here to count 0 to 6 when we do this. Alright, so we should be able to understand that, and I want you to understand, remember the MSB to LSB is backwards. The MSB is X4, the LSB is X2 up here probe-wise, okay, but you can see that those probes are attached to the output Q of each flip-flop. So it's very, very imperative that we understand the difference between the MSB and the LSB here so that you can control the count. Okay, so let's look at the next example. So I'm going to stop this one. I got the next example pulled up here. Alright, so we have this mod counter. Everything's kind of set up the same. This little bar I have going down here that's just going to a probe. Just kind of show you, just trying to set everything up. It's just going to probe so I can check and see when the circuit goes. So I've labeled this one. We're going to count from 1 to 4. Alright, so I'm changing the starting value. So that's important here. And how do I know I'm changing the starting value? Well, look at that first flip-flop. I've tied it to VCC. Okay? Now, what you have to pay attention to is what am I starting at? I want this count to start at 1 instead of 0. So that way I have to understand what I'm doing here and what's going in opposite. So notice at the bottom of these flip-flops here, these are all inverted signals. Okay, so whatever I send in here each time, okay, is going to invert that signal. So that 5 volts actually inverts to 0, and the others are 1s when we go in. So still, it's MSB to LSB, so we're looking at 0, 0, 1. We read this right to left when we do this, so 0, 0, 1. So that's going to control that I'm going to start at 1. Now the first cycle through, it's not going to show you that because we've got to get into the counter. The first cycle will still show you that we're starting at 0 because that's the digits that's going to come through as the clock comes through. Okay, and then how are we controlling 4? Well, 4 is 1, 0, 0, but remember we have to do count plus 1. Okay, count plus 1. So since 1, 0, 0 is 4, we have to do count plus 1, so we're going to tell it to reset at 5, so 1, 0, 1, which means I should be pulling at the top here a 1, a 0, and a 1. So if I trace back, okay, my first red right here is tracing back to the MSB, that's my A. Notice how I have these flip-flops labeled in the middle, A, B, and C. Alright, so when I rewrite my truth table, it comes out the other way, right? I write it as A, B, C, left to right. But my MSB here is Q4, okay, or X4, sorry, and I'm getting a 1 there. And then I trace the green line back. The green line back is going to Q bar on the second flip-flop, which indicates a 0. And then I trace my other red back, and I'm pulling out of Q1 out of the first flip-flop, so I'm pulling out of Q there. So that means I'm pulling out 1, 0, 1. Well, 1, 0, 1 is 5 in binary, and I want to reset at 5. So I want to start at 1, so that's 0, 0, 1. That's the bottom. That's the clears. So the clears are going to control where you start, okay? And then the output Qs are going to control where you end. Essentially, if you want to take a look at this. All right, so if I take a look at this count, remember the first time through we're going to see a 0, and then from then on out it's just going to go 1, 2, 3, 4. And you can really watch that ripple effect propagate here on the 7-segment display, you know, as we're going through. So if I take a look at the count here, we're at 1, and then it'll switch to 2. And I've lowered my frequency down to 50 Hertz, like I said, so that you can watch this. Remember, your default frequency is very high, so it's going to like really toggle through all those quickly and play with your eyes. But, you know, watching the probes, so now, all right, we're back to 1. So we're just going to consistently go 1, 2, 3, 4. And you can watch the ripple effect, you know, on from the 7-segment display through each character. But make sure that you're paying attention to the probes here at the top. Remember, everything's kind of backwards as you read it. And I can't emphasize this more. The flip-flops are left to right in series, but the most significant bit is on the far right, the least significant bit is on the far left. So it's backwards as you read this. All right, and you can flip them around on your schematic if you want to, but essentially this is 1, 0, 0, okay, and then when we read it the other way, this is 0, 0, 1, which is producing a 1, okay, and then we're going to have 0, 1, 0, which is producing 2, then you're going to have 0, 1, 1, which is producing 3, and then we're back to 1, 0, 0 here in a second, which produces the 4. So just remember that this is your MSB, and you've got to interpret these opposite the way they're coming out of here. I could have easily drugged these probes and put them in a nice order, but I wanted to leave it this way so that you understand how it's coming out of the flip-flops. Okay, and then when we're going in down here, remember it's opposite, so we're assuming a 0, a 0, and a 1 is going in because we want to start at 1. Okay, so this modulus is 1 to 4. So since I needed to make it up to 4, I had to have at least 3D flip-flops to run this. If I only had 2D flip-flops, you know, I could run it and it would automatically go 0 to 4 for me, and I could control where it's going in as well. But ideally, it's a little bit better if you want to design it this way. All right, let's take a look at the last example. So I'm going to stop this one, and I'm going to pull up my last mod counter here. Okay, so I'm going to set all this up, and I want you to see, you know, and I always kind of label what it's going to do so that you can understand here. It's going to count from 3 to 6. So I'm changing the starting value. All right, and this counter, if I were to just use this counter as is, it would go 0 to 7, but I want to be able to control what's going on. All right, so we're going to go 3 to 6. So, and then as we take a look here, okay, as we go through this, this is, remember, this is controlling, this NAND gate over here is controlling, you know, when it's going to reset. So if I trace each one of these back, you know, my A is, I'm pulling out a Q from there. My B, okay, if I'm pulling in here, I'm going to pull out 1, 1, 1. So you notice I'm going to be pulling from the Q from each one of these flip-flops. Why 1, 1, 1? Well, I want it to start over at 6. 6 is my count, all right? 6, 1, 1, 0 is my count, but I have to do count plus 1 to tell it when I want to reset. So that's why I'm going to tell it to reset at 1, 1, 1. Okay, so that's my reset, that's my NAND. And I said I wanted it to count from 3 to 6, so I need to start at 3. The only way to do that is set my clears to 3. But remember, I've got to go MSB, most significant bit, which is the last flip-flop, to the first flip-flop, which is the least significant bit. So when I read this, I'm going to go 0, 1, 1. Okay, I'm going to read this looking oppositely, right? 0, 1, 1. Okay, is 3 in binary. So this counter should count from 3 to 6. So it's very important that A is, the clear for A has to be 0, the clear for B has to be 1, and the clear for C has to be 1, okay, as they go in. So that's going to tell us that we're going to reset, or not reset, we're going to start at 3, which is 0, 1, 1 in binary. Alright, so let's go ahead and simulate this. So there's a small ripple effect that we've got to get through as it clears through the registers here on the flip-flops because of that first clock. Alright, but then we're going to continuously cycle through 3 to 6 here. Alright, so it just takes it a second. We got to get through the ripple effect, all of that, and we'll see that this is going to continually count. Alright, from 3 to 6. So there's our 6. We're going to hit our reset, okay, and we're going to start at 3, and then we're going to go 3, 4, 5, 6. Alright, so these are going to be some labs that you're going to do in class. I want you to, you know, still make sure that you follow the procedure and develop everything, but I wanted to be able to, you know, explain this for those of you that might be doing this at home or things like that, to really understand, you know, how the count is going and how we control the count. Alright, so remember the reset, we're going to pull from either Q or Q bar on each one of the D flip-flops, send that into our NAND gate, and then the output of our NAND gate has to go into our clears when we want them to clear. If we want to control where we start, alright, we want to control where we start by, you know, controlling the clears at the bottom. So in this case, we want to go from 3 to 6. Alright, so we have to make sure that we are at 0, 1, 1. right? Remember, 5 volts is signifying a 1, 1. And I know this isn't schematically like the most beautiful thing, but I wanted you to really see. So that's why I wrote the separate VCCs there. They would connect all to one VCC. However, I just wanted to show you, what's going on there. Now, the other thing that you have to pay attention to is notice every time I have a VCC down here connected to clear, what did I do? I took the output of that NAND and I replaced it to the presets. Okay, so we have to be opposite signals there. So it's very important. I didn't talk about this on the mod 2 counter example, but on this one, it's the same on the mod 2. If you go back and look, the one that has VCC into the clear, that one has to get the reset. Okay, so wherever you're sending in VCC, so if we were putting VCC all in the top, okay, all the output of the NANDs would go into the clears at the bottom. But anytime I drop a VCC into the clear at the bottom, the NAND has to replace it going into the preset. So notice the most significant bit, the D flip-flop on the right, notice how the NAND gate's going directly into the clear. Well, at the top, the VCC is going into the preset. Alright, so you got to make sure that everything's opposite polarity there when you do this in order for your counts to work. So make sure, this will really kind of help you guide along and understand this as you build these circuits in Multisim and cycle through them. Alright, as usual, email me with any questions. Else, guys, we'll go through this a little bit more in class, and you guys will have plenty of time to work on this in class. Alright, guys, have a great day. I will see you in class.